Greetings everyone. I'm Sharda Tripathi and currently I'm serving as Assistant Professor at Birla Institute of Technology and Science, Pilani in India. Today I'm going to present our work titled VERA, Resource Orchestration for Virtualized Services at the Edge. This work has been accepted at the Mobile and Wireless Network Symposium IEEE ICC 2022. Along with me, the co-authors in this work are Corrado Puligedu, Somrita Pramanik, Andres Garcia Saavedra, and Carla Fabiana Cesarini. This is the outline of my presentation. First, we will see the background and motivation of the problem, followed by system architecture and working of the VERA framework. Subsequently, I will present the performance results and conclude the presentation with future research directions. So let's begin. Network function virtualization and edge computing, as we know, have entirely transformed the delivery of mobile services across the network architectures. Basically, they enable third parties to partner up with mobile operators in order to directly reach their customers and deliver a plethora of services. These have been shown to improve upon the classical service measures, for example, enhancing the QoE, reducing the latency, jitter, bandwidth consumption, and also providing for local data storage and processing. To name a few examples, video streaming, gaming, virtual reality, IoT, etc. are the services that can benefit from the combination of network function virtualization and edge computing. In that sense, we can clearly say that these are serving as the pioneers of modern day 5G networks. However, there are certain challenges which inhibit us to exploit this technology at its full potential. First of all, network edge has limited resource availability, and when both virtualized user applications and network services need to be concurrently supported, a natural conflict in resource usage is bound to arise. Secondly, the heterogeneity of virtual services leads to complex dependencies between the amount of data that each service has to process. Also, for best user experience, almost all of these services have to meet really stringent performance indices. So in such a scenario, wherein we have resource scarcity, designing of automated and efficient resource orchestration mechanisms is very critical, and that is also the key objective of this work. Further, from the state of the art, we identify that the existing works do not consider the interdependence or non-trivial correlations between different virtual services at the edge. And considering the dynamics of the network along with the dynamics of service traffic increases the complexity of the solutions so much that it becomes difficult to integrate them with the ORAN architecture. Thus, in view of these limitations, we have designed VERA, short for Virtualized Edge for Radio and User Applications. It is a flexible reinforcement learning framework for joint allocation of computing and radio resources across user applications and network services at the edge. Besides this, other key contributions that we make are, we show that the decision-making process in VERA is Pareto efficient and fair with respect to all the virtual services hosted at the edge. We also provide a proof of concept through containerized edge and an SRS LTE-based test bed. Also, we compare our approach to the benchmark scheme, and around 60% improvement is shown in the CPU budget violation rate. Here, I would like to emphasize that almost none of the existing works have considered resource allocation at the edge for both network services and user applications together. They target either the network services or the user applications. And we also show that our work can be very well integrated with the ORAN architecture. With this, I will introduce our reference scenario. So for the sake of clarity, we focus on one user application, which is the livecast service, and one virtual base station implemented within an edge computing platform. The VERA controller is deployed in the SMO, which is the Service Management and Orchestration platform, and it interacts with the ORAN RIC, Livecast Controller, and the NFV Virtual Infrastructure Manager. In this way, VERA's workflow are fully compliant with ORAN's machine learning procedures. The framework of VERA controller is designed using a model-free reinforcement learning approach, and it includes distributed learning agents, each agent corresponding to a service in the edge platform. These agents simultaneously make decisions for the allocation of radio and computing resources, as well as tune in the service-specific operating parameters. We collectively refer to these decisions as the radio allocation policy. The VERA framework has two development stages. Firstly, the greedy analysis. In the greedy analysis, each reinforcement learning agent makes a decision based on the shared context representation to obtain a greedy resource allocation policy. The variables in the shared context representation for a monitoring slot includes normalized video and radio throttle time, video input encoding bitrate, video input frames per second, video input resolution, livecast network load, and the channel quality indicator value. Further, to extract the correlation between the context variables coming from heterogeneous services, an autoencoder projects the context vector in the slide shown by variable X onto its latent representation shown by variable Y over here. This variable Y in turn is shared with each of the reinforcement learning agent, which is making decision corresponding to different services hosted in the edge. The decisions for the livecast services are made for its CPU allocation, video output encoding bitrate, and video output encoding frames per second. So these comprise the action vector for the livecast service. Similarly, for the VRAN, the action vector includes the radio CPU allocation and the choice of modulation and coding scheme. To facilitate the learning, we have formulated our reward function for each service as the sum of reward observed through its KPIs. For the livecast, we have considered the state of client buffer and the weighted VMAP score as the KPI, while for the VRAN, these parameters are latency and the segment error rate. Individual KPI rewards are formulated using error function ERF as shown in equation 3. The idea of such formulation is that we intend to keep the observed KPIs as close as possible to the target KPIs, failing which the system may perform better at the cost of extra resource consumption. And that is clearly what we want to avoid. Then in the second stage, the greedy policies from all the reinforcement learning agents are collected and further refined such that the CPU budget constraints is met, thereby entailing a fair Pareto efficient resource sharing. For this, we formulate a constrained multi-criteria optimization problem as shown in equation 4. So here gamma k represents the criterion function, which is actually the reward of the kth service following a given resource allocation strategy S. UK are the set of coefficients wherein the value of UK is greater than equal to 0 and the summation of UK over all the services is equal to 1. BC here denotes the total available CPU budget. This optimization problem shown in equation 4 is solved using an iterative search and update algorithm, which we refer to as algorithm 1, shown on the next slide. And we mathematically prove in the paper that the solution obtained through algorithm 1 is Pareto efficient and fair with respect to each service. Also, we prove that algorithm 1 converges at a sublinear rate. For the purpose of reinforcement learning, we are using differential semi-gradient SARSA over the time horizon. This is the representation of algorithm 1, which we call as the fair Pareto efficient CPU allocation algorithm. Next, I summarize the working of the VERA framework. So initially, we have a context from which we generate the shared space representation. This is shared both with the livecast as well as the VRAN agent, and they give as output the greedy allocation policy. Subsequently, the greedy policy is fine-tuned by the Pareto block such that the CPU budget is met, and the final solution is Pareto efficient fair for both the services. Next, I will present the results as we obtained in our experiments. First of all, the convergence evaluation. So from figure 3 in this slide, we observe that for both livecast as well as VRAN, the KPI rewards are saturating close to the maximum value, which is 1. The convergence of livecast service is relatively slower due to its slowly varying dynamics. So this demonstrates that VERA framework has efficient learning capability despite the heterogeneity of the context vector and the action set. Then we analyze the KPI performance, and as shown in figure 4, for both the services, barring a few initial iterations when the algorithm is actually learning, the KPI targets are always met. Thus, we can say that VERA's choice of actions lead to KPI satisfaction for both the services. Next, we investigate a scenario by varying the CPU constraints. So here we have considered two cases. First one having 2 virtual CPUs and the second one having 3 virtual CPUs as the CPU budget constraint. From figure 5 on this slide, we observe that the reward is higher for 3 virtual CPUs, although the difference in the performance of 2 and 3 virtual CPUs is very marginal, which indicates that VERA can meet the target KPIs in the presence of stringent CPU constraints as well. Finally, we compare the CPU budget violation rate of VERA with an independent multi-agent reinforcement learning approach. It can be observed from table 1 on this slide that unlike VERA, for IRL, the CPU budget violation rate increases as the constraints tighten further. A mean improvement of 60% was observed in the CPU violation rate of VERA compared to IRL. Thus, we can say that the Pareto block is a significant component in order to ensure fair Pareto efficient solution across different services. To summarize, in this work, we have proposed VERA, which is a distributed learning framework to jointly allocate radio and computing resources for both user applications as well as network services at the edge. We have shown that the resource allocation policy is Pareto efficient and fair with respect to all the virtual services, and the proof of concept is designed using containerized edge and SRS LTE based testbed. From our experiments, we show the feasibility of VERA framework and its excellent performance in the presence of capacity constrained resources. An average improvement of 60% in CPU budget violation rate was observed with respect to the closest competitive technique for resource allocation in capacity constrained edge scenarios. As the future work, we are investigating the scalability of VERA in multi-service, multi-user VRAN scenarios, and also considering multiple resource constrained variables. That was all from my side. Thank you so much for your attention.